So this is our Senior Design 2 project review PowerPoint. Over the course of the semester, our team converted a traditional mountain bike into an electric pedal assist bike. And through the duration of this presentation, we intend to show the audience just how we did that. So the motivations and objectives coming into this build were as follows. We wanted to produce a sound product for under $500 that would encompass several features that would distinguish our product from similar products like it on the market. And the way that we went about achieving this was by implementing an automatic gear shifting circuit and developing an application that the rider can use to personalize their riding experience. And here's a photo of our final design implementation. You can see that the majority of the hardware is mounted to the bike's chassis, and we found that this design decision maintained the rider's ability to pedal while utilizing the space that was available to us with the bike's shape.
Here's a quick video of us using the bike. Right now the gear shifter is not implemented, so it's a bit difficult to pedal.
It's raining!
It was raining.
And the system block diagram kind of just shows what's going on in the back end for that build. You can see that the majority of the arrows are directed towards the Raspberry Pi or away from the Raspberry Pi. This suggests that this controller is the primary brains of our system. This is what establishes a Bluetooth connection between all of the sensors, the user's phone, as well as provides Bluetooth serial data to the ESP32, controlling both the motor and the gear shift motor.
The battery management system, or BMS, is able to handle up to 50 amps of discharge current, which is sufficient for the battery, which can output a maximum of 48 amps. As well, the charge current is sufficient for the battery, which has a capacity of 16 amp hours, and at 0.5 C, 8 amps of continuous current are required to charge the battery. To the right, we see a wiring diagram of the BMS, with B plus going to the positive terminal and B minus going to the negative terminal. B plus goes to the positive terminal of the motor and P minus goes to the ground of the motor. XT90 connectors are used with 10 gauge diameter. To the left, we see the LR2170SA cells that are used in the battery with 1.5 by 8 millimeter nickel strips. These strips can handle up to a maximum of 9 amps, which for 4 strips in series totals to a maximum of 36 amps safely able to discharge. The motor controller can output a maximum of 30 amps peak current to the motor. So this is sufficient. To the right, we see the mounted battery and BMS.
Target current plus an offset, the driver is turned off, which causes the current to fall and match the target current, and the cycle will continue from there. The circuit was also designed to target a particular negative current for braking when enabled, but because I broke the motor driver in the final week of our project, we were unable to test our ability to target for a specific current when braking. On the bottom left, you can see the current limiting logic discussed in the previous slide. Above that is the cadence sensor. This sensor works through the use of a digital Hall effect sensor. The sensor counts each time one of the 12 magnets from the disc passes by. Every 100 milliseconds, the motor controller has an interrupt, which triggers a Bluetooth communication routine. This routine includes a conversion from ticks per 100 milliseconds to revolutions per minute of the pedals. This sensor is integral for our bike's automatic gear shifting and pedal assist features. This is because we target a specific 60 to 80 RPM of the pedals in our gear shifting, and we only want to apply the pedal assist whenever the user is actually pedaling. In the middle, you can see magnets secured to the sprocket of the back wheel of the bike. These trigger interrupts in an identical way to the cadence sensor. The ESP32 motor controller similarly converts ticks per 100 milliseconds into miles per hour. This information is meant to be sent to the phone for display and should be used to limit the speed in different assist modes. For example, limiting the speed of the pedal assist to 20 miles per hour as required by law. However, due to a bug in our system, this information is not being utilized properly. On the right is the motor driver used in our final prototype. This is due to the component failure in the motor driver we designed and built ourselves. This driver is limited to 10 amps, which is a lot lower than we originally intended. It receives a PWM signal from the motor controller to supply the motor with the desired voltage and current.
Okay, ready? It's on none right now. Should be no assist.
Yep.
And on low.
Goes kind of fast.
That's okay. That's low, and then medium. Faster. Okay. And then high. Even high. And then none. There you go. So these are the two pages for the application. The first page on the left is what the user will see when they open up the application. The first thing that the user would need to do is enable permissions. These ask for specific Bluetooth connection permissions in order to establish the connection. And then they can turn Bluetooth on or off with the button, and that Bluetooth logo on the top will have an X over it if Bluetooth is not currently enabled. And then the user will press pair with bike, so this will establish all of the connection between the Android device and the Raspberry Pi. So once that connection is established, then the user can hit next, and it'll take you to this second fragment. This reports speed, distance, and battery percentage, and allows the user to press a level of assist that they want for the pedal assist function. So no assist, a low, medium, or high, and toggle the automatic gear shifter, which is by default off. And then once they are done, they can hit the power down button, and this will close any socket connections and close the app. This is kind of the workflow of what happens within the application. So as I said earlier, the user enables permissions, so it checks what permissions are currently enabled that are required and then requests them. If the user approves all of the requests, then the user can continue to press buttons, but if any permissions are denied for a second time, then the program exits. Then the user can press Bluetooth on or off to turn Bluetooth on if it is not on already, and then they can press pair with bike. So what this does is it starts discovery, it looks for the MAC address of the Raspberry Pi, and then once that is found, it then creates an RF comm socket connection between the device and the Raspberry Pi, and then a thread is used to manage the input and output streams for writing and reading data from the socket. Basically, one thread is constantly reading the input stream to check for any data, and the writing only occurs on specific button presses that happen later in the application. So the data that comes in is used for the speedometer, the odometer, and the battery image. Once the user has fully established the connection, they can press next, and this can allow them to press those buttons that I said before to enable the pedal assist, to toggle the gear shifter, and power down. On any of the levels of assist, it sends non, low, medium, or high based on whatever button they pressed to the Raspberry Pi so that the Pi can calculate specific targets. On error at any point within the code, the socket connection is closed, and then the program exits. So the Raspberry Pi acts as the main brain of the bike. It communicates via Bluetooth to the main motor controller ESP32 and to the Android device. It communicates serially via USB to the ESP32 that controls the gear shifter. So the first thing that it does is that it reads in the speed, distance, voltage, and cadence from the motor controller ESP32. This information eventually gets passed on via Bluetooth back to the app to provide that information to the user. Then it reads in data from the application if any buttons have been pressed to enable any of the features, like the pedal assist or the gear shift. Based on the level of pedal assist, it calculates voltage and current targets and then sends that back to the motor controller ESP32. Again, if there's any error in the code at any point, the socket connection gets closed and then the program exits. So the gear shifter is connected to the Raspberry Pi via USB. It checks if any serial data has come in from the Raspberry Pi. This happens when the automatic gear shifter is enabled. Basically, the logic within the Raspberry Pi is that it gets measurements from the cadence sensor. An ideal cadence for cycling is between 60 and 80 RPM. So if your cadence is above 80 RPM, then it will try and shift down, which will make it more difficult to pedal. And if your cadence is below 60, then it will shift up to make it easier to pedal. So the Raspberry Pi sends the word up or down based on whatever the cadence is. And if there is serial data available, then it will call a clockwise or counterclockwise rotation functions that rotates for a set duty cycle with a delay in the right direction. But if the automatic gear shifter is not enabled, then no serial data will be sent from the Raspberry Pi. And the same functions are called, but instead they work on an interrupt based on the buttons on the handlebars as shown in this picture on the left.
This is a video of our demo of our gear shifter.
As for how everything performed, any controls from the app that would cause hardware changes would take less than only a second, and the pedal assist itself would activate after 100 milliseconds after the user starts the pedal. There were quite a few struggles faced throughout the process. Learning the inner workings of a new language in Java was somewhat time-consuming on its own. Bluetooth connectivity was an incredibly difficult task on the software side, being far more time-consuming than anticipated. Soldering was also quite time-consuming and an overall tedious process. There was also difficulty in tuning the PID. In the future, we'd really like to implement a regenerative braking system and a DIY BMS, as well as a more interactive app and faster charging batteries would ideally be integrated.